All right, so welcome back for section 11.2. In this section, we're going to take a look at something called contingency tables. All right. Now, we'll get to what a contingency table here is in a second, but our key concepts are we're going to be analyzing contingency tables, which can include frequency counts for categorical data arranged in a 2x2 table. Okay. 2x2, that doesn't mean 2 rows, 2 columns. That means variables. We'll talk a little bit about that more here in a second. Right? In this session, we're going to take a look at how we can run a hypothesis test to check to see if the variables that we're looking at are independent of each other. Now, we're going to take a look at test number 1, that is a test for homogeneity. But depending on how far down this rabbit hole you go, you might end up doing a test 2, which is a Fisher test, or a test 3, which is a McNemers. I always struggle with that name, McNemers. The Fisher exact test is the test that we'd use if you had a really small sample. If your data wasn't big enough to run a standard homogeneity test. And the McNemers test is the one used when you have matched pairs. I want you to think back to chapter 9. Remember when we had those dependent samples and we tested hypotheses about the befores and afters? Like the shoes, did they make you jump higher? Or did the test prep make you score higher? That's when you would use a McNemers. That's a match pairs testing. We're not going to do either of those here, but just so you know, they do exist and they take care of some other situations that we have to deal with. All right, but let's get into the meat of it. We're testing contingency tables, but what the heck is a contingency table? Well, this is a contingency table. A contingency table, also called a two-way table. Me personally, I like two-way table a little better, but okay, I get it. It has a name, contingency table, as well. Basically, it's a table that consists of frequency counts of categorical data corresponding to two different variables. Okay? One of the variables is going to categorize your rows, and the other variable is going to categorize your columns. So here, our row variable is the gender identity of the individual, and our column variable is the favorite way to eat ice cream. Right? And so what we end up with is we end up with this table full of data that we went out and we surveyed people. We asked them, how do you identify? And what's your favorite way to eat ice cream? And we counted it all up and threw it in this beautiful table. Now, the question that we have is, these numbers that are in this table, are they dependent between the variables that they represent, or are they independent? Let me zoom in a little bit and let's talk about one of them. Suppose I pick this number 158 here. That number 158 is the number of people who identified as female and said they prefer to eat their ice cream as a sundae. Now the question is there dependence between the two responses, that is, that they would identify as female and that they would have a favorite way to eat ice cream, or are those values in there, specifically the 158, is it independent of those two things? Right? Now, to get to the root of this, we need to go back a ways. So hopefully you remember there was a formula we had that said if A and B are independent of each other, then the probability of A and B, events A and B occurring, is just the probability of event A multiplied by the probability of event B. So if we said that A was identify as female and B was the favorite way to eat ice cream was a sundae, then the probability that someone would say that they're female and favorite way to eat ice cream is a sundae should just be the probability that they're female. So the probability of F and sundae should just be the probability of someone being female multiplied by the probability of sundae. If these two events, that is, remember, female and sundae, are dependent, then these would just not be equal. Right? So we're going to test that. But we're not just going to test it for one cell in this table. We're going to test it for all of them. Right? So the test for independence we test a null hypothesis, and the null hypothesis is that the row and the column variables are independent. That is, there's no dependency between what you choose, how you choose to eat your ice cream, and whether you identify as male or female. Right? So our objective is to Our objective is to conduct that hypothesis test. The hypothesis test of independence between that row variable and that column variable. So for us, in this example, we'd be conducting a hypothesis test of independence between gender and favorite way to eat ice cream. Right? We got some notation we're going to use. We're going to use O still, same as before. It's going to represent the observed frequencies, but not just for that one set of values, but for all the values in the table. We're still going to have an E. Our E is going to represent our expected frequencies. And we find our expected frequencies by assuming that the variables are independent. Right? R here is going to count rows, and C here is going to count columns. So for our problem that we were just looking up here, R would be 2, C would be 1, 2, 3, 4, 5, would be 5. The cup, cone, sundae, sandwich, and other. I'm not sure what other is here. Maybe milkshake? A cup or a cone or a sundae or an ice cream sandwich. I mean, maybe like an ice cream bar, like one of those vanilla bars dipped in chocolate or something. I don't know. Yeah, that wouldn't fit any of the categories, so that must be other. Okay, so there's our notation. The requirements are similar to what they always are. Random. We have to have sample data as a table, and we have to be big enough. And again, big enough here is that the expected frequency must be 5. There's no requirement for the observed frequency. It's just the expected must be 5. Our null hypothesis is always that these things are independent, the row and the column variables. Our alternate hypothesis is that the row and column variables are dependent. When you write these two right here, you could swap out row for what it is. In this case, we could write in that the gender and the favorite way to eat ice cream are independent, and then the alternate would be that the gender and the column variable, the favorite way to eat ice cream, are dependent. Okay. All right, the math. What's going on behind the scenes? Well, the formula is exactly the same as the formula that we use for the chi-squared goodness of fit test. It's the same formula. There's just more here. There's more there because it isn't just a single column of values for the O's and a single column of values for the E's. It's an entire table for the O's and an entire table for the E's. Right? When we run that test and we do all this math, that math is going to give us a chi-squared value, and that chi-squared value is going to show up somewhere on our chi-squared distribution. If it shows up over here, we're in the fail to reject region because it would lead to a p-value that is much bigger than the the alpha level. And so we would say fail to reject the null, and we would assume that it's a good fit with the assumed distribution. Or in this case, the good fit with the assumed distribution means that we are looking at, we have evidence to suggest, or we don't have enough evidence to say that they are not independent. Okay? If our ends up out here, if our chi-squared value ends up out there, we're in the reject the null, and so we would assume that there must be some sort of dependence going on here. Right? All right, so let's take a look at what they mean by expected frequencies. Right? So this table right here, the one that they gave us, all of this right here, this is observed. They went out and asked people questions, they gathered this data. Now, if we were to assume that this relationship was independent, then every single cell in here, right? So since this is our observed, we need to build the same thing for our expected. So we need to create another table down here that's going to have a row for male, a row for female, a column for cup, a column for cone, a column for sundae, a column for sandwich, and a column for other. And then I need to find numbers to put in this cell and in this cell and in this cell and in this and this and this and this and this and this and this. And those numbers in all those cells need to be the expected count for that cell, assuming that everything is independent. So every single one of those cells down there, if we assume independence for this, needs to be a product of two probabilities. It needs to be the product of the row probability times the probability of the column, and then we need to multiply it by the sample size so that we can get that count for that row. Right? Now, how do I find these? Well, I'm going to go back up here real quick and do some partial sums. Now, I know that the number of males, or people who identify as male, is 1,069 because I added it up. I know that the number who identify as female is 1,128. Okay? It's just the sum of these rows. That means that the probability of male should be 1069 out of, well, a grand total here would be 2,197, so out of 2,197. I also know that the probability that someone is identifying as female would then be 1128 out of 2,197. Okay. I can find partial sums for every column as well. Okay. The partial sum for this first column over here is 504 plus 474, so that's 978. Here we're looking at 688. Here we're looking at 300, what is that, 340? Here we're looking at, what is that, 88? And over here we're looking at 103. So that means that the probability that someone would pick cup should be 978 out of 2197. The probability of cone is 287 out of 2197. Do you see where this is going? Probability of Sunday, SU for Sunday, would be 340 out of 2197. The probability of sandwich, SA, would be 88 out of 2197. And the probability of other would be 103 out of 2197. Right? So now that I have all of the individual event probabilities, that is the probability of just male and don't care about ice cream, just female, don't care about ice cream, just cup, don't care about gender, just cones, Sunday sandwich, and other, all not caring about gender. Those are the blue ones. I can use those to find all the values in this expected value table down here, this contingency table for expected values. So I can go here to this first entry, the one that says male and cup, this one right here, right? And I can say that this guy needs to be the probability of male multiplied by the probability of cup multiplied by 21, what was the size of the sample? 2197. And then I'll move to the one to the right. That's going to be the probability of male times the probability of cone times 2197. And then the probability of male times the probability of Sunday times 2197. And then the probability of male times the probability of sandwich times 2197. Last one's going to be the probability of male times the probability of other times 2197. You see where this is going? I'm going to pause and I'll be right back. So then the female row, which I wrote in red, would just be replace all the probabilities of males with the probability of females to find all those values. And then that would give us our expected value table, right? So then we would look at it and go, I don't know what number this is, but how does this number compare with 504? And how does this number compare with 287? And how does this expected compare with this observed, and this expected, and this observed, and so on and so forth through all 10 values in this table. So this formula right here, this O minus E that is hiding inside those parentheses, that's the observed, that's our count. And then these are our expected, that's our formulas that we just wrote. And then we take the count minus the formula, get an answer, and square it. Count minus formula, get an answer, and square it. And then we're adding all these things up. And we're adding them up, and we're adding them up, and we're adding them up, and we add them up. If the counts and the expecteds, if the O's and the E's are far apart, chi-squared is big, puts you out on this tail. If the O's and the E's are close together, chi-squared is small, puts you over there on that side. And we fail to reject, or we reject that null hypothesis. Now, I know what you're thinking. Oh my gosh, that's a lot of work. The beautiful thing is, we never actually have to do this. Luckily for us, the good people at TI expected that you would have to do this, and they built it into the test. Okay? So let's take a look and see how this works. So our example here is we are supposed to use that sample data and a significance level of 0.05 to test the claim that gender is independent of the favorite way to eat ice cream. Okay? So our claim is gender is independent of favorite way to eat ice cream. Okay? That means that our null hypothesis is that gender and favorite are independent. Our alternate hypothesis is that gender and favorite way are dependent, and our claim is the null. Okay, all right. So I'm going to get the calculator up, so pause here for a second. So let's look at the test on the calculator and see what data it wants. So I'm going to go to tests, and now I'm going to use not that chi-squared goodness of fit. I'm just going to use that chi-squared test. All right? So I'll enter, and look, it wants the observed as a, and what does this mean? Where it's got like a brace around it, and then it says A, and then a brace around it. All right. So that's the calculator. That's the TI speak for a matrix. Okay? So when the calculator sees data like this, okay, the calculator ignores all of the header rows and column labels, and it just sees a bunch of numbers and says, look, that's a matrix that has 2 rows and 5 columns. So I'm going to take that data and input it into my calculator as a matrix. Now, right now it's currently saying the observed is in matrix A, so I'm just going to stick with that, and I'm going to put this data into the calculator as a matrix. Okay, so I'm going to quit out of here and get that data in first so I can get ready. So over here on the left, you see where it says matrix just below the math key and above the x to the -1 key in blue? That's a second function, so I'll second function and go to matrix. It's already highlighting matrix A, which is the first matrix. Don't worry if yours doesn't have 2 by 3 written there, because I've used it before, that's why it's got it. If you've not used it before, that won't be there. And I'm going to scroll over to edit, and I'm going to edit matrix A. Okay? First thing I need to do is I need to change the size of the matrix to match the size of my data. The fancy way to say this is to adjust the dimension of the matrix. Okay? The first number is the number of rows. It's set at 2, we have 2, life is good. Then I go over to the second number, which is the number of columns. It currently says 3, we have 5, so I'm going to change that to a 5. Now, it doesn't look like it changed anything, but you might have noticed over here on the right-hand side, there's now these weird horizontal lines. That just means that this matrix is bigger than we can see on screen, and it's just off the screen. And if we scrolled right, we could scroll into those new columns. Right? All right, so first row, first column is 504. And then first row, second column is 287. And then we're looking at a 182. And then 43. And then 53. Second row, 474. 401. 158. 45. And 50. And so there's my data. Now this is the weak point, and I put a lot of stuff in, so I'm going to check it twice. That last column should be 5350. That looks good. 4345. That looks good. 182, 158, 287, 401, and 504, 47. Okay, that looks good. So I've got my data in the calculator. Now that I've got my data in the calculator, I'm going to go back and run that test, that chi-squared test. Right? So is the observed in matrix A? Yep. It says expected in matrix B. Basically what that's telling you is not that we need to put the expected in B. What it's telling you is that it's going to find the expected and put the expected in B if we wanted to see it. And so I'm going to go down to calculate. I run the test by running calculate. You'll see that I've got a chi-squared value there. That chi-squared value there of 20.07, that is the test statistic. What's more important for us is our p-value. Our p-value there is that 4.84 times 10 to the negative fourth. So that means our p-value is 0.00005. 48 rounds to 5. Our alpha level from the problem was a 0.05. If I compare this to that, I would say that p is much smaller than alpha. When p is smaller than alpha, we reject that null hypothesis. But the claim was the null hypothesis that they were independent. So then our answer to this would be, there is enough evidence to reject the claim of independence. So that means most likely that the way that you like to eat ice cream is somehow dependent upon your gender identity. Now, that would be a sociological question. I can't answer why that could possibly be. But I've got data that says reject independence. And if we're rejecting independence, that pretty much means dependence is the answer. All right, so this is a chi-squared test for independence. For some reason, we want to test to see whether these variables are independent of those variables. Let's take a look at another one and see if we can see where it's going on here. So a health club manager, I want to point out something. Look, we're almost done. We've got one more page after this, and then we'll be done with the entire semester. A health club manager wants to determine whether the number of days per week that college students exercise is related to gender. So they want to find out whether their variable number, whether the variable number of days per week that someone works out is somehow related to gender. Are they dependent or are they independent? A random sample of 275 college students is selected and results are classified as shown in the table. At a significance level of 0.05, is there enough evidence to conclude that the number of days a student exercises is related to gender? Okay. So what's the claim here? Well, the claim is that the number of days is related to gender. So the claim is that we're looking at dependence here, right? Our null is always that, in this case, gender and number of days are independent. Our alternate would be that gender and number of days are dependent. Our claim is the alternate this time. Okay? All right. Our data is that table up there and a significance level of 0.05. That's our data, right? So we need to run the test on this, but just like last time, before I can run the test, I've got to get the data into the calculator. Looking at this data up here, it looks like that's the data right there if we remove the labels. So we're looking at a matrix that is a 2x4 matrix, right? It's a 2x4 matrix because it has 2 rows, male and female, and 4 columns, the 0 to 1, 2 to 3, 4 to 5, 6 to 7. All right, so I'm gonna go ahead and put that data in. So I go second matrix. Oh, hey, look, see how B's there now? Let's look at it. Those are the expected frequencies for the ice cream problem, if you needed to know them. I don't need to know them, but maybe, I don't know, maybe someday I'll need to know them. Okay? So I'm gonna go ahead and edit my matrix A to put my data in. I need a 2x3 matrix. My first row is 40, 53, 26. Wait a second, I screwed up. This isn't a 2x3, this is a 2x4. But look how easy it was to fix that problem. I just go back up, change the 3 to a 4, slops another column in there, and I can put in the data. Second row, 34, 68, whoa, 34, enter, 68, enter, 37, enter, 11. Okay, again, putting it into the room, I make my mistake, so I'll check that last column, 6, 11, 26, 37, 53, 68, 40, 34, that looks good. Okay, so I'll quit out of there, go to stat, over to test, looking for that chi-squared test, observed as in A. Now there's other data from before in B. I don't need to worry about that. The test, when we run it, it'll clear out the old data and put in the new data, and it won't mess with anything. So I never have to fix that. I never have to go delete that matrix or clear those values out. I can just let it be. I'll go ahead and calculate. Now, if you're interested and you need it, the 3.49 there is our chi-squared test statistic. What's more important to us is our p-value. Our p-value is 0.322. Okay. When we compare p to alpha, we see that p is greater than alpha. When p is greater than alpha, we fail to reject the null. Okay? But now I got a problem. If I'm failing to reject the null and the claim was the alternate, what does that mean? So hopefully you got it memorized. If you don't, you could reference back to that table. When I'm failing to reject the null and the claim is the alternate, I say there is not enough or sufficient evidence to support the claim of dependence. Now, like we've done before, if you wanted to, you could bulk that statement up and say the claim that the gender and the number of days that a student works out are dependent, or I'm just going with claim of dependence. All right, we're looking at 30 minutes here or so, so I'm going to end this one. We'll come back for our last video, and I'll see you back here for that one. Have a great one.